introduce the last speaker for today. I'd like to introduce Chris Eagle.
Why aren't you on
Okay.
Twitter?
Why am I not on Twitter?
Yeah.
I am.
He's on Twitter. I don't know what his Twitter handle is. I'm sorry. I seen a
I'm
bunch
hard
of
to
Chris
find.
Eagles
I'm
out there,
not-
so I didn't want to just grab one. There was no photos that I saw.
That's what I was.
So Chris Eagle is a senior lecturer in computer science at the Naval Postgraduate School in Monterey, California. Computer engineer scientist for 28 years. His research interests include computer network operations, computer forensics, and anti-reverse engineering. He has been a speaker at conferences such as Black Hat, Infiltrate, ShmooCon, DEF CON, and author of the ID Pro book. In his spare time, he is the Dean of Hacking for the School of Root, past championship of DEF CON, Capture the Flag, and a core member of DT Tech, the most recent organizers of DEF CON's CTF. Put our hands together. Welcome, Chris Eagle.
Thank you. Thanks. Haven't given this talk before. Don't know how it's going to go. You're welcome to gun me to as much as you like. Steven's chance to pay attention. See if you can catch me. No. Thanks. I'm classically trained. I don't know if that's going to. We'll see. There you go. Before they're loaded. Too late. So today I'm going to talk about reverse engineering demystified is what I'm calling it. Daryl said to talk technical, talk non-technical. It's trying to be a little bit of a mix. I understand we have a mix of people in the crowd, from CS majors up to CIOs or network administrators, etc. So we'll see how this goes. Feel free to stop me anytime to ask questions. I don't mind doing the sidebar. I often get sidetracked for far too long, and that'll definitely eat up all the time. Don't have too many slides. So there's a little bit about me. Spent a lot of time playing CTF, organizing CTF. I'm out of that business finally, and I'll actually get to enjoy DEF CON for the first time ever. I think I haven't left the CTF room in 13 years. I've seen about 2 talks in that entire time, I think. Daryl covered my research interests. I'm really interested in obfuscated code analysis and ways to automate getting through obfuscated code so we can get on to the real analysis of what's going on. You see that in a lot of malware. That's my Twitter handle up there, is @school. So for anybody searching for me, that's where you can find me. Not terribly interesting feed. Mostly a read only for me, and there's my email if you really want to get a hold of me. Do work for the government. Obligated to say that nothing I say should be attributed to them, especially since I just took a 20% pay cut starting this week. So I'm not too happy about that. Scope of the talk. This is the outline. I'll talk about what I'm going to talk about in a minute. We'll go through what is reverse engineering from my perspective. A lot of mythology surrounding reverse engineering, what it can and can't do for you, what is and isn't reverse engineering. I get pretty semantic about it. Talk about why we do some reverse engineering, how we do some reverse engineering. Again, this is all going to be fairly high level. I'll talk about some tools and techniques, but nothing too deep, I don't think. Hopefully, no deep theory that passes over everybody's head or that I have a hard time understanding. Some applications of reverse engineering, challenges of reverse engineering, and a little bit about perhaps the future of reverse engineering or the tools that are coming down the pipe and what promise they may hold. So, did I say one?
Yeah, it was very slight.
Yeah, it wasn't even like a U and an N, it was just a U. Is this a gun or an gun? Let's clarify that. Okay. So the scope, I'm going to really narrowly focus on software reverse engineering. I don't do hardware reverse engineering or system reverse engineering, that kind of stuff. I'm really just a software guy. So we take bits and bytes and we turn them back into code of some sort. Talk a little bit about decompilation, so that's sort of the next step, and I'll show you a really high-level overview of the reverse engineering sort of path. Talk a little bit about dynamic techniques rather than static techniques, and we'll break that all down. So why do we reverse engineer? From a high-level perspective, we reverse engineer things to gain a greater understanding of things for which we have no design information. So if somebody drops a binary in your lap and you've missed that whole software engineering flow, or you sit down and you do requirements analysis, you miss the whole design phase. These are where you're documenting things that should lead to each line of code, right? You shouldn't have code in a project that doesn't derive from some requirement that you can point to in the very formal projects. Okay, so we start off this design process. That drives the development of some source code. I've left out the waterfall or the whatever model you want to put in there, the spiral model where we loop back and maybe we redesign as we encounter different problems. So we say we get some source code that satisfies all our requirements. We're going to then build a system out of it. Usually the output that we see is going to be some executable, some binary file format on the tail end, and from the compiler somewhere in there, maybe you can envision that it passes through an assembly language state. They often skipped over. We don't generally generate the intermediate assembly language on purpose and then build our code from that assembly language. So the compiler sort of handles all of it for us. But you can envision that in the middle there, it sort of passes from the source state to an assembly language state, and then finally on to a binary state as it goes through a traditional compiler to assembler translation, assembler to binary translation. And then reverse engineering is going the other way, starting with the thing on the right. All you have is a binary with no design information, and we're trying to get closer and closer to the left edge of the slide. In an ideal world, I would recover the complete design specification for the piece of software that I'm taking apart, and that's a fantasy world. And that's never going to happen because at each phase of this process, you start to lose information. Okay? Not intentionally, maybe intentionally, but our requirements aren't captured in our source code, only as actions, not necessarily as statements, unless we're very, very disciplined about copying the plain language of our requirements into our source code in the form of comments. Okay, so you may see that in well-structured source code where there's a lot of discipline being applied in the software development process. But imagine that you're losing some of that already. If you go pick up the source code on a typical project, you're not going to be able to extract out a requirements document from that source code. From the source code, let's include that assembly language translation. Okay, what does that assembly language translation, the compiler? Compilation, and I'll get around to this later again, is an extremely lossy operation. Okay, gone are your comments. Gone are your local variable names. Gone are some of your global variable names, perhaps. And what is left is, in this case, a massive assembly language, but if we just skip through that, we're going to have just a binary. Okay, so how do we go backwards, and what information do we get back? Certainly we're not going to get comments back anywhere along the way, and we're not going to get variable names back anywhere along the way. And in general, you're never going to get that design document back. Okay, so we're looking for tools that get us up this chain. Right? First and easiest, I'd like to get some assembly. Maybe I'd like to get some source. And again, in this fantasy world, I'd like to recover the entire design document. It kind of depends on what my use case. Why am I doing reverse engineering? Well, sometimes I just want to learn how something works. Okay, that's it. This thing has fallen into my lap, and that kind of covers everything, right? We really want to learn how something works, and from there move on to perhaps more specific uses of our reverse engineering skills or our reverse engineering requirements. Maybe you want to do complete design recovery as opposed to a partial recovery. If I'm looking at a piece of malware, I don't really want a design document on that malware. Somehow I want to drill in and find the piece that is malicious, the piece that does communications, so that I can figure out how to write a signature or how to defeat this thing or what new technique they're using to achieve persistence as soon as they achieve execution on, say, my Windows system. Okay, I want to learn these two new techniques and extract them. I don't want to go rebuild the malware necessarily. But maybe I want to do a compatible product, right, top to bottom. Okay, maybe I have an obsolete product and I need to re-engineer that thing. I had a case fall into my lap the other day, F-18 cabin pressure controller. They built on an old 88 system and they want to update these things. They don't make them anymore. Okay, Navy's still flying F-18s, okay, but they have no supplier for these parts. Right? So there's an outfit, there's a Navy lab that this is their current task, is to redesign, re-engineer the F-18 cabin pressure controller. And they don't have design documents for it other than looking at the source code that they extracted off the firmware. Okay, that's an entire re-engineering effort that may involve, upgrading it to at least 486s off of these, 8088 architectures, we hope, maybe something better, and then re-engineering that code from the 16-bit code to 32-bit code, something like that for a whole new system. Modernizing existing products, okay, that could be the case. They may not want to add new functionality, they're just trying to modernize. Sometimes you want to both modernize and add new functionality. You want to modernize and fix a problem that's in there. You are literally re-engineering the thing. And in that case, it's entirely possible that they could lift the code, they could understand the firmware, they could understand the hardware, they could just mimic everything and be perfectly satisfied to have this 8-bit F-18 cabin pressure controller. After all, it's been working for 30 some odd years, however long the F-18 has been flying. If we can just start cranking these out, effectively starting up the assembly line again, we're just fine. Okay, but maybe they want to add new functionality into this. Maybe there's been a long-standing design deficiency. It wasn't critical, it wasn't going to ground the aircraft, but maybe they want to add capability, so they're going to be re-engineering. They probably want to get back to source code because it's much easier to add capability in source code than it is to jam something in the middle of a binary blob, okay, to add new capability to a product. Okay. Maybe we want to verify the operation of something. Does this thing do exactly what it's stated to do, nothing more and nothing less? Okay, so does it do everything? Does it have any backdoors contained in it? I don't know. Okay, how do you know? We don't know. We get no assurances from Microsoft that their products work as advertised. We get no proofs of correctness with any of the code that is delivered to our commodity PCs. Okay, so how do we know? What kind of verification process? Really, reverse engineering is our only way to go about doing that. So how do we do all this? There are two primary approaches to the reverse engineering problem when it comes to code. You have static techniques and you have dynamic techniques, and then of course you can develop hybrid approaches. Okay? But the idea is to try to understand exactly what's going on with this thing. Okay? Neither of these techniques tell us what something does. Okay? This is the big fallacy with reverse engineering. You throw something in IDA, IDA doesn't tell you anything about what the program does. You throw it in the best decompiler in the world, that decompiler doesn't tell you anything about what that program does. Okay, there are no tools out there that will say to you, that is a rat, okay, that is a web browser, okay, that is a backdoor, Trojan, keylogger, whatever. Yes?
We'll tell you if it's inside of a for loop or a while loop.
We'll get to that. So the question was, will it tell you if you're looking at code that's part of a loop, perhaps a for loop, while loop? I'll talk about some of that, and we'll talk about some of the techniques. It doesn't. In some cases, yeah, they'll openly say so. In the case of a decompiler, you're going to see maybe a for loop in the code. In the case of a disassembler, because you don't quite get up to that high-level language that has for loops and things like that, you're going to have to use some other cues. But they're graphical cues that will clue you into the fact that there's a loop present. So we can get those basic code flow constructs, but we can't tell why it's looping. Is it computing a sum here? Is it computing an average? We don't know why. Okay, that's entirely up to the human analyst, and that's where things really slow down. Okay, so you want these tools, you want automated recovery of the assembly or of the source, but beyond that, it's up to you. So when somebody walks in and says, I'm great at using IDA, okay, but yeah, can you read the assembly code? Can you tell me what it's doing? How are your interpretation skills there? Okay, because it doesn't mean anything to run IDA effectively, okay, but to analyze the code effectively is what you're looking for. That's the same at the source code level. That's the same at the assembly language level. When you have an established product or a program and you're looking to hire a new programmer, you'd like to know if they can come in. They could be the best C programmer in the world, but if they can't come in and digest those 10 or 100,000 lines of code and jump into the project, they're never going to be of use to you. Okay, so what skill sets are you looking for? Somebody they know how to use IDA on their resume. Be careful. Right? Start giving them an x86 quiz or whatever architecture it is you're really looking at using IDA for. Obviously, if you're not using IDA in your projects, then that's a useless resume bullet. So how do we help the human, right? We lift things to levels that are easier for the human to digest. And that's why we use disassemblers and decompilers. And binary is not so easy for a human to digest. Okay? Tools such as IDA Pro, the main disassembler that's out there. There are other ways to get disassemblies. It's not the only one out there, but it's one of the predominant ones. We'll lift things from machine language up to assembly language. So you need people that are fluent in assembly language to figure out what's going on. It's easier to read in machine language, that's for sure. Decompilers will try to lift things from machine language, okay, up to some source code. or source-like code. Most decompilers don't claim that you're going to be able to take their output and feed them right back into a compiler and get the same input that you fed through initially, right? We don't go from machine language up to source, run it through a compiler, and get right back to the same machine language. Okay? Essentially impossible to do. Because decompilers have a lot of signatures, for lack of a better word, that try to profile the compiler that was used to create the original binary, lift it to some C, and then if it's truly C, you could feed it through any other compiler and get back down to an equivalent binary. But without the same compiler options, or if you used a different compiler, you can't expect to get the same machine code output from that tool. Okay, so right now, again, Hexraise is the decompiler add-on to IDA Pro that most people are using in this space. And there are some others out there. I'll talk about them towards the end. So disassemblers more specifically. Got to have a disassembler that matches up with the architecture you're interested in studying. Okay, and more these days we're getting embedded microcontrollers and all kinds of systems that you don't find a lot of quantity, right? So you may not see assemblers, mainstream assemblers out on the market for them. Okay, x86 assemblers all over the place. ARM, there's a little bit less. Okay, MIPS, Spark, all this other stuff, fewer and fewer. IDA comes with a lot of different disassembly capabilities, okay, but you'd be hard for us to find tools that do all of the other different architectures that are out there. Okay, Raspberry Pi, whatever the Video Core 4. Right, no disassembler capability out there really. People have written it up as an IDA add-on, okay, but you're going to have a hard time finding it other than that. Okay, so you got to match your architecture. Hopefully it understands something about the image format that you're going to throw at it. Okay, real easy in the case of standard executables, ELFs that come off of Linux systems, PEs that come off of Windows systems, Mach-Os that come off of OS X. Okay, real easy. A raw binary blob of firmware, a little bit more difficult. What's the structure there? I mean, the main challenge that a disassembler faces is what's code and what's data. Hey, how does it know? Right? It's all just a bunch of bytes. A disassembler's got to know where to go to start turning code, machine language opcodes back into assembly language and be able to know when to quit, be able to know which of those bytes are data, shouldn't get turned back into code, so you don't end up with really strange looking disassemblies. And that's where something like IDA is very handy because it does a pretty good job of understanding the division between your code and your data. Assuming we can find code, everything's pretty straightforward. If you gave this to a CS1 programming student and you said, here's some input, it's just binary, I need you to generate an assembly language listing, they'd probably do something along the lines of a table lookup, right? Opcode in, machine language out. You get something like that. That's about the best graphic I have in my entire presentation. I was not an art major. Read an input byte. We get 41. We have to know, is it code or is it data? Because if it's data, I want it to look like define a byte over on the right, and if it's code, I want it to disassemble as an instruction, increment ECX over there on the left. Is it a multi-byte instruction set, right? As opposed to a fixed length instruction set. Fixed length easy, I'm reading 4 bytes at a time perhaps. Okay? 4 bytes, table lookup, here's your instruction. x86, you read 1, you gotta figure out, do I need more? Do I need more? Do I need more? Could be 1 byte, could be 30 bytes. Question?
How do you deal with segment pointers or descriptors? Is that also one of those concerns?
It is a concern. So with 16-bit code, for example, your disassembler has got to have some sort of idea of some default segment register values so it can understand, am I doing near calls or far calls?
Right.
Right? Am I dealing with 16-bit addresses or 24-bit offsets, right? Segment plus offset, etc. And so that's all, you have to build that into the logic of your disassembler.
Would that be in the format of the file that you're looking at, telling you what those segment pointers might be?
No, not typically. So, for example, when we lift a firmware off of a 16-bit machine, 16-bit x86, if we know where the reset vector sends us, if we have a pretty good idea of at least what's the first instruction, the first thing that happens on reset is, we got to really look at the code and pay attention. Okay, first instruction is loading the CS register with 40.
Yeah.
And now the disassembler needs to carry that state forward. It actually is beyond now just a table lookup. It's got to start remembering some state, or things are just not going to make sense.
Okay.
Right? And when it doesn't do that, you may have to educate it. IDA lets you play around with it. That's one of the nice things about IDA, as opposed to just text-based disassemblers that just spew text out, and you can't tweak the parameters to it very easily. So, all good questions, right? And difficult problems to take care of. Decompilers. I still call it an evolving field because there's really only one, or there has been one out there for the last, 5-6 years. Same people that make IDA have put out the hex-rays decompiler. Just saw one last night somebody tweeted about, I can't remember, it's called the C4 decompiler. They don't know where that's going, haven't had a chance to play with it, but it looks like an open source or at least freeware decompiler that's coming out. There's somebody wrote it's literally called IDA decompiler as an add-on to IDA. Okay, so there's starting to be some competition with the hex-rays decompiler, which is quite expensive. And hopefully we'll see that field grow, and it'd be nice to see some competition. One of the biggest problems that I have with decompilers is it's much more difficult to tell if it's right. How do you know? Right? You're staring at 500 bytes of assembly language and you say decompile this function and it spits out some C. How do you know it's right? You're trusting all the algorithms of the person who developed a decompiler. Again, there's no proof of correctness that it didn't miss anything. Not every instruction gets represented in there. I'm not going to get into the weeds about calling conventions and things like that. But the stack pointer is being manipulated in the assembly language, and you say, why isn't it being manipulated over here in the source code? Right? They have to account for different calling conventions, different compilers, etc. And it's a really, really difficult problem. And I would say it's the least accurate form of code recovery, right? Much less accurate than disassembly. Disassembly is a lot easier to walk through if you really wanted to. Byte for byte, and say, yep, that's represented as instruction, 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 that one's data, and you could go through and match up all the bytes that you see in the file with all the bytes and their assembly language representation that you're seeing in your display. Really hard to do that in a for loop. Hey, which one of those hundreds of assembly language instructions is the beginning of the for loop? Right? Which ones are the increment phase?
Or if they unrolled the loop.
Yeah, if the loop gets unrolled, okay, where we just paste copies of the loop one after another, and they try to collapse it back into a for loop, something like that. Okay, and this gets into the skill of the decompiler author. Okay, often decompilers have very specific techniques built in for very specific compilers. And so you find that in the case of hex-rays, it's very good against Visual Studio Code. It's pretty good against Borland code. But when you start to get away from those two compilers, because those are the two that they study the most in-house, their accuracy starts to wane. Okay, they can't handle C++. They can't handle every architecture. They do have an ARM version of the compiler out there right now, but if you're looking at something other than x86 or ARM, you're sort of out of luck as far as decompilers go. And so it's not. Question?
Is the motivation for this basically to get closer to the original design?
It's so you get expansion from source code to assembly. I can just throw out a number and say, roughly for every line of source, you're talking about 5 to 8 lines of assembly. Okay, so instead of looking at 500 lines, I'd rather of assembly, page down, right? There's no really great way to visualize it. Maybe I can collapse that down to 100 lines of C. And it's to get closer to something that's platform independent, that is less specific to the architecture. So now I don't need x86 gurus. Now I can bring in and I can have people that are proficient in C start studying the code and working from there. So I bring a bigger knowledge pool to bear on the problem. Did you have a question here?
No, I was just making fun of the fact that there's no PowerPC version.
Yeah, no PowerPC decompiler.
Oh.
If Apple hadn't migrated, maybe there'd be one nowadays. So, let's see. Very compiler dependent, least accurate form. Okay, no proof of correctness. That's my big hang up. I've seen plenty of cases where there's been behavior missing from decompiled versions of the code. And so if you are really trying to recreate the original system, that's not such a good thing. Now, I'm kind of a dinosaur. I just stare at assembly. I've been doing it since before decompilers came out, and that's just my comfort level. And it's become second nature. It's takes some time to get there, but people can do it. Okay, so things you got to remember about compilation, right, and its impact on source recovery, right? Decompilation. I already talked about some of these. Compilation is a lossy operation, right? We lose our comments, we lose local variable names, right? So you're never going to see that stuff get recovered into the source code. Gonna stretch that out. You don't split things back into the original files. He's sleeping over there.
She's not. She's thinking of it.
So you're looking at a big binary. This thing probably originated from some number of source files, 10, 20, 50 different source files across a very large project. When you say decompile, you get one monster decompilation. It's not going to get split back out, so you're left to refactor the thing however you want to do it. There's no boundaries that get determined there because all that stuff is gone. We don't know what portions of code came from what file. And you may get library code compiled in there. If you've never looked at a binary, it's not just the code you wrote. Compilers paste in a ton of support code. And I'm not just talking about like libc kind of support code. Okay, there's glue code that gets you from the entry point of the program to main, right? If I ask a room full of people, where does your program begin execution? I'll even grant that you wrote the thing in C. And we're talking about the assembly language, machine language level, I'd still get a lot of people that said it begins at main. That's not remotely true. There's a lot of stuff that has to happen before main even begins executing. Main is a C function, and your operating system does not care that your program was written in C. So there's got to be some massaging of the way the operating system sets up your process state, and with your argc, your argv, your environment strings, which differ in the Unix world, and they're different on FreeBSD, they're different on Linux, OS X, and they're very, very different on Windows. But all of that data has to be massaged and packaged up into what main expects, which is our traditional three arguments of argc, argv, and the environment pointer. Okay, in very specific locations in a very specific arrangement. Okay, so all that glue code has to happen, and it has already executed before main ever executes. Okay, so all that's piled in, and sometimes you get other library stubs piled in there, and that's going to show up in your decompiled code. Right? Unless you have a very good decompiler that knows, oh, that's library code, I'm going to leave it out. Because if you want to recompile it, that's just going to get built back in. Right? That's all a side effect of the fact that you're calling malloc or something like that. Okay. Just because you get this stuff doesn't mean we understand a thing. I've already said that. Okay, and this is something that managers tend to forget, right? They think IDA is this big, expensive tool. They've heard all these great things about it. So I've had too many people say, we got this piece of malware, let's open it up in IDA so we can find out what it does. You're not going to find out what it does unless you have a human sitting in front of it who can, if they're really good, they can look at it in almost any tool. Okay, but IDA is not the be-all, end-all of analysis tools. In fact, it's not an analysis tool. It's really just a view into the binary. Right, the human has got to do the analysis, can make annotations, can maybe make IDA show us things in different ways, can make it easier to understand, but IDA doesn't analyze anything. Okay, same with your source code. Right, you can throw that at other analysis tools and maybe get some extra information out of it, but you're not going to have this instant understanding just because you think you got a good source code recovery. Okay, so we've got to maybe make use of other tools that will make it easier for us to understand things. So things, there are graph-oriented tools out there that look something like this. And I'll start to, these are all my IDA sessions for different examples in here. All right, so you've got, there's a simple disassembly. Is that font big enough? IDA's not so great with fonts in the back. Can you guys read that? It's not really important what it all says. Suffice it to say, that's a disassembly listing. Okay. There's not a lot of structural features shown there. Is there any branching? Yeah, if you know how to read IDA over in the left margin, there's some arrows that indicate that things might branch around. But we can throw that up, and we can get a graph view of this thing. And IDA's got this graph overview. IDA's actually really behind in the sort of the graph viewing space. If anybody knows Halvar, he has a tool called BimNavi. His company Dynamics put this tool out a number of years ago. They've been bought by Google. You can go get it. It's much cheaper than when Halvar was selling it. But the whole point of it was some people process things better in a graphical sense. just looking at the block diagram, which doesn't contain any code, it's pretty easy to see that we've got a couple of if statements up top. If else, right? I can go two ways. And as we move over here down and to the right, that heavier blue line indicates some kind of looping construct. Okay, so in a graphical sense, it says, yeah, I know what my control structures are. And then we have to fill in the blanks. When you break things down like this and you see things in a display like that, those blocks there, we call those basic blocks. It means that once you're in one, you don't get out of it until you reach the end of the block. So all the statements in there should be fairly easy to turn back into simple source language statements, assignment statements, things like that. What's not happening inside of any of the blocks is any other branching of any kind. Because branching would terminate the block. If there was a branch, the block would be split down, and we receive the control structure there, where the branch goes. So this is very, very helpful. And using these graphs, this is called a control flow graph, is one of the things that decompilers rely heavily on to infer whether we're talking about an if statement, an if-else statement, is there some kind of looping construct, and so on. Now the problem with decompilers is, and people get hung up on this, that loop, what is it? Is it a while loop? Is it a do loop? Is it a for loop? Who cares? Right? You should have learned in CS1 that you only need one looping construct, because from that one looping construct you can build every other looping construct. People get way too hung up on trying to get back to the original source code, especially in looping constructs like that. It just doesn't matter. Right? Might be an if statement, wrapping a loop, could have been a do loop, could have been a while loop, doesn't really matter. The important information that's conveyed here is that there is in fact a loop. All right? So there's these kind of graphs, and then where's another binary to look at? This is one function, right? This is the control flow inside of one function. So we can go over here and look at kernel 32, right? This is a function within kernel 32. It's just got a lot of branching. Branch, 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 branch. Eventually you work your way down to the end. Hey, there are other ways to look at things, other ways to graph things. And IDA has finally built in something called a proximity viewer. I'm going to close down some of these other windows. And this is the higher level here. But that green function, which is sort of the node that's in the middle there, this is a function-based view. Right? These are functions calling other functions. So it helps us see the interrelationship between different functions without telling us the specifics about what's going inside any one block. It's like a call graph. And you can prune this thing, you can go deep, you can go shallow. But if you go too deep, it gets much too difficult to follow. You have functions calling functions calling functions. If you descend down a call tree, that tree can get huge. Question?
Those circles that they happen to have there, those are just labels?
No, these circles these correspond to the pluses. Right? So this is
But it's not
the view of the entire graph, which is too big to fit into the view here. And all those circles are telling us is that there are other references here that we could expand. Right? It goes deeper in that direction, or it goes higher up or higher down, but we're trying to keep our graph from being too cluttered. Okay? So graphing, offers another capability for assisting you in understand what's going on, what functions call which functions, and so on.
And what's that dotted line for around that whole block?
Let's see, which one are you looking at?
You can see in the window.
Well, that's what you see in the window.
Oh yeah, so the dotted line right here,
Yeah.
I can grab that and it will scroll, and that's exactly the viewport around the larger window that doesn't fit, and I can shrink that down and throw that up. But, okay, the purple ones are library functions and so on. So that's just IDA trying to tell you that it's pretty smart. Okay. So those are some static approaches, right? We didn't run the thing at all. We fed them through some tools and we got some output, and maybe that helps us understand what's going on. Then you can take a more dynamic approach. We call this black box analysis. It's very much like modeled after what is done on the hardware side. Feed some input to it, see what happens. Okay, so that's what we do with the program. We generally build some kind of sandbox environment, very heavily instrumented environment, and we run the program, see what it does. Maybe it's very obvious, maybe dialog boxes are opening up, maybe it's just Microsoft Word, and you say, okay, I can make it show me that screen, I can build those menu items, I can add all those drop downs. And we keep tickling it until we think we've uncovered all the behavior, but that just tells us what it does. That gives us a more high-level specification. It doesn't tell us the logic that underlies it. We know that when I do this, this action happens, and we have to add in the glue code that makes that work. And we have to figure out when I change the font, what is the underlying code that actually makes the font change in, say, the Windows operating system? Yes.
Do you have to run the black box several times because of the limitations that Dijkstra says that if you have machines running, you can't imitate two machines can't, yeah. You know what I'm talking about, all right. So do you have to run it several times?
You typically do run it several times. Typically, you do some differential analysis, you do some tracing, trace recording. What happens is we run it once, and we record everything that happens and say, okay, that's the startup code. We set that as a filter because we're not interested in that code anymore. Run it again, filter out all of those events. Start doing mouse clicks. Find out what happens over there. So we do that, and we do all kinds of instrumentation. That's just observing, say, in one program. Then we can observe the external events of the program as well. Okay, so in the case of malware, people who do malware analysis throw that malware into the sandbox. They've got all kinds of network monitoring going on. They've all got all kinds of file system monitoring. In the case of Windows, we've got registry monitoring. When I start up that process, you may see nothing happen, right? Nothing observable. Okay, but packets are flying, registries getting changed, files are getting created, maybe new processes are getting created, and we need to make sure we record all this information. Okay, but that doesn't tell us, we learn that from the outside in, and you never know in this case, or it's very difficult to tell, whether you got 100% coverage of the code. We can instrument, and we can say, did every instruction execute at least once? And we can say, yeah, well, we hit every instruction, but did we get every behavior? Don't know, right? Some of those instructions might be in a loop, and those instructions need to be run 50 times before it ever exhibited a particular behavior. And there's no way to know that until you just do it and do it and do it. What are the inputs? You just never know. Okay, so while this can tell you some high-level behaviors, it doesn't necessarily tell you the order in which they occur. It doesn't expose all the logic behind the behaviors. How are they making that happen? We just know something happened. Difficult to automate, useful for clean room approaches. Right, if you were going to do a clean room implementation of, say, Microsoft Word and build a word processor, you'd probably want to take this approach because you're not looking at the code and you're probably won't end up ripping off blocks of code. Yeah, it's going to look functionally equivalent, but under the hood, it shouldn't look the same if you don't cheat and peek at the underlying code. Okay, whereas the static analysis approach, where you've been reading reams of assembly language, it's very likely that some of that will migrate into your design. Okay, so if you're worried about that kind of thing, here's what you need to do. Or you have one team look at the assembly language, try to lift to a design specification which you hand to another team that re-implements without ever having the influence of seeing the underlying code. Right? These are all the things you have to worry about if you're worried about the legalese. So where do we apply all this stuff? We already talked about some cases, but maybe you want to build compatible products. Samba is a great example of this. Samba was a pure reverse engineering effort. At the time it was initially developed, Microsoft was not remotely forthcoming with any of the protocol specifications for Samba. And so those guys reverse engineered literally everything. Okay, pretty impressive effort. Maybe you just want to learn how something works. Okay, we want to know how a piece of malware works. We're not trying to build a compatible piece of malware. We're not trying to re-engineer the malware. We just need to know how specific features of it work. You don't even care about 90% of it, perhaps. Something like Skype, which was a proprietary protocol. If you want to build compatible product with Skype, you need to know how that protocol works at a minimum. So you want to drill into Skype and find out where are the protocol handlers and decipher that protocol. Maybe this is the first step in a re-engineering process, right? We got to reverse engineer it and get it to something that we can work with to re-engineer. Or maybe, in some cases, people are looking to detect theft of intellectual property. There's been a tremendous number of GPL violations uncovered because people reverse engineered something and realized that you've got, pick a library, libjpeg, something, libpng, embedded, statically linked into purporting a proprietary piece of code. Okay, so you see this all the time, people detecting GPL violations, or one company saying, you stole my code, there it is, and so on. I think that was at the heart of what Oracle versus Google and the Java APIs, a lot of that. How about vulnerability discovery? A lot of people say, well, we're going to do reverse engineering for vulnerability discovery. It gets a special slide of its own just because everybody likes to talk about it. this is not strictly speaking reverse engineering. I don't think. Right? You may use reverse engineering to facilitate this. I'm going to lift to assembly language, but it's the analysis that you add on top of this, I suppose. Right? This could be your use case, but it's not reverse engineering by itself. You do some reverse engineering in the case in vulnerability discovery. Although there are ways to find vulnerabilities where you don't do any reverse engineering at all, which I'll talk about under static and dynamic approaches. Right? So modern static approaches may never generate a disassembly. Right? You just feed the binary to it, it does some analysis, it does what we call symbolic execution, comes up with a bunch of crazy looking formulas, feeds into what we call a theorem prover, and the theorem prover says, here's an input that will crash this program. Okay, it's pretty impressive mathematics. There's a lot of people looking at this stuff. Microsoft's got a pretty powerful tool called Z3. If you're into theorem proving and constraint solvers, you can. A lot of people have worked their product into their symbolic execution engines. Dynamic approaches typically involve an approach called fuzzing, which many of you may have heard, and that's basically find an intelligent way, preferably an intelligent way, to generate some inputs that we're going to throw at the binary. And hope the binary crashes, and if it doesn't crash, generate another input, try again. Right? Return, lather, rinse, repeat, around and around and around we go, and we hope that at some point we get some crashes out of it. We save the crash dump, we go manually analyze the crash dump, understand why it crashed, don't know anything at all about the behavior of the program. All we know is that with this input, that thing crashed, and if I tweak that input, then I can take control of the program. And knowing very little about the program. So depending on the approach that you take to your vulnerability discovery, you may have done very little reverse engineering. And we may have very little to no understanding of what the program really does. All we're happy to have is an input that crashes it. Okay? And we're even happier if we can tweak that input so that we can gain control of the program. Hybrid approaches may combine the, not fuzzing, but actually running the program as an instrumented, concrete instance of the running program, and use what you learn in that running program to feed the theorem proving side. Okay, so on the symbolic side, you're making a lot of guesses, or you're overgeneralizing the behavior of the program. Okay? Instead of overgeneralizing all the time, we take some specific instances, some concrete information out of the running instance, feed it to the theorem prover to help it narrow down the scope, make it easier for it to find some solutions. And as a result of all of this, there are some academic claims. I'll just ask you to Google CMU Mayhem if you're interested, of people who have built systems that do automated exploit generation. So not only do they find the vulnerability, but they spit out a working exploit to take advantage of the vulnerability. Okay, Carnegie Mellon, they've got a program up there, a research program called Mayhem. So far they're not releasing it there, but they're making lots of claims. Technical challenges, technical obstacles to reverse engineering. Challenges to reverse engineering. You have technical challenges, and then you have a lot of legal challenges. The technical challenges are the easier ones to overcome in many cases, and the legal ones, well, I'll talk about those in a minute. A lot of obstacles to reverse engineering, things that can get in the way. People don't want you to know what they're doing in their code. There's lots of things that they can try to do. All of these have proved, if not easy to bypass, at least you can get around them eventually. Okay, but the types of things you'll see are code obfuscation, okay, where somebody, in most cases, their binaries are being post-processed, so the compiler's already done its job, you got an executable in hand, you're going to feed that to an obfuscation tool, which is going to reach in, and in the simplest cases, it just compresses the code, okay, and adds a decompressor stub, very much like the way viruses work, right? Tack on some code at the end, redirect execution at startup to your decompression stub instead of your malicious stub. The decompressor gains execution, decompresses the original code, and jumps into it. Okay, what's the impact on you? Throw it in IDA, and all you're looking at is compressed data, which IDA can't disassemble, right? Because the real code doesn't exist until runtime, and IDA has no runtime context with which to evaluate the code you're looking at. See, non-sequential flow of code, which means you're jumping into the middle of instructions, self-modifying code. Unrecognized instructions is a new popular one, figuring out some undocumented instructions in any architecture and then using those. A lot of them are NOPs, but they're undocumented. using those in their code, and then your disassemblers don't know what to do, right? How, especially in x86. Here's this opcode. How long is it really? 2 byte, 4 byte, 10 byte? If it thinks it's a 5 byte opcode, but it's really a 1 byte opcode when it comes down to it, then there's going to be some desynchronization, I call it, of the disassembly. And we can see some of these effects in simple binaries like this one, okay, where there's IDA's best effort at disassembly. Right? Start 0, that's essentially the entry point of this program. That is the first instruction that will execute once the loader has finished loading this process and transfers control in here. And then you can see what we got. Nothing. Right? So we're supposed to believe that that's all this does. Okay? Probably not, right? We believe that it does more. But the problem is, once we get down to right here, okay, IDA doesn't know where execution goes. You have a conditional jump right there. It can take one of 2 paths. Okay, IDA assumes it's going to flow into the next instruction, so we get this crazy VXD call. Hey, virtual, I don't even know what that is. That's some 16-bit instruction that you never see, should never see in 32-bit code. But IDA knows, or the instruction says that if the jump's not taken, or if the jump is taken, we're going to jump 2 bytes into that instruction. And I know that because IDA's given me a label right here. Right, you can see the yellow highlighting. Okay, so when it says that label plus 2, that means 2 bytes into that instruction. That VXD call spans, so I'm just going to use the last 2 digits, from address 14 to 1A. That's 6 bytes. And so this instruction, if the branch is taken, jumps right into the middle of the next instruction. Well, IDA has no context information. Is the Z flag set right now, or is it not set right now? IDA can only disassemble it one way or the other. Okay, so now what do you have to do? Right, things get very manual at this point. So your best disassembly tool in the world has failed you, and you have to say, well, look what happens here, right? We're subtracting ECX from itself, right? Something minus itself is 0. Okay, so to you, a little bit of observation, we know that the Z flag will always be set there. That's really an unconditional jump. And so we have to sit here and start monkeying with the code. We undefine it, and we define a new instruction right down here, and now the jump resolves. Right? Those 2 bytes in the middle, those data bytes, are just that. They're data bytes. They get skipped. Okay, but IDA has no way to know that. Right? So our job becomes much more manual. Okay? We lose the luxury of having a fully automated tool to recover our code. If we want to really break this down, you go up here in the top. Okay? It's hard to see. There's the gray bar, and then you see the olive color over there. But what you want to see up there is a lot of blue. Okay? That's the bytes within our binary. Okay? Progressing from our lowest virtual address on the left towards higher virtual addresses on the right. Okay? There's no blue up there, which means IDA hasn't recognized any functions in this disassembly at all. Why not? This is obfuscated. Okay? It's not just that it's jumping into the middle of instructions and IDA can't disassemble the thing. If we go far enough, we'd find out that there's a lot of self-modifying code in this, and a lot of that is compressed or encoded or whatever, and we have to go through. In this one, there's probably 30 some odd decoding loops. It does incremental decoding. Right? So you decode it a little bit, you get some code back, work through that, realize it decodes some more, They're like nuisance features, right? You can get through them eventually, okay? But the first time you see this, it's not fun. Yes?
When this obfuscated code is expanded by the built-in assembler, or whatever you want to call it, does it go back into encoded form, or does it just stay resident in memory expanded?
When it's expanded by IDA?
No, when most people write their code and they obfuscate it, and they've got a section that they call up.
Mm-hmm. Okay.
Do
So-
they re-encode it, put it back, or just leave it?
Yeah, so the question is, once a binary's been obfuscated, it does some self-modifying. Once it's decrypted itself so that it's back to its original form, does it re-encrypt itself when it's done? And the answer, some do and some don't.
Okay, so it's.
Okay, it depends entirely on the obfuscation system that you've used. Some obfuscators let you actually tag your source code with macros, like function enter, function exit.
Yeah.
And they'll expand those macros so that on entry you decode the function, and on exit you re-encode the function. Okay, and the reason for doing that is, from the obfuscator's point of view, you never want the entire program image decoded in memory at any one time, because it's too easy to go take a process snapshot using an in-circuit emulator or debugger, freeze the system, grab the memory, and then you have the entire process sitting in the memory space somewhere, and you just need to go pick it out. Then you can analyze it in its de-obfuscated fashion.
Right.
So on and on this one goes, and this one's no fun. This was a virus called SoBig, if anybody remembers that one. And then you have anti-debugging techniques. So you say, well, you know, if it's self-modifying, I'll just run it. Right? I'll set some breakpoints, and I'll try to catch it, and when it's run far enough, I'll just do a memory dump. Okay, so there's a lot of techniques that aren't really anti-disassembly at all. You can disassemble them just fine. It's just code injected into the binary that asks the question, is the debugger running? And if it's running, I quit. Right? Before I ever decode anything, before I ever jump to any of that decoded memory. Are things taking too long between any two instructions? Right? Do some timing checks. If it takes too long, maybe you're single stepping. I quit. Right? There's a lot of ways to try to detect the debugger. You set software breakpoints. So you go in and you put a CC. CC is an int3. Right? Software breakpoint into memory somewhere down the road. You better not put it in a region of memory that's going to get self-modified, because then your CC won't be a CC by the time you get there, and the program will probably crash. And if you do have it down in memory, you better hope that the program doesn't do some checksum over that range of bytes, because that CC probably wasn't there originally, and the checksum will compute incorrectly. That can be detected, and the program will shut down. In the Windows world, we see a lot of cases where they intentionally generate exceptions. They intentionally divide by 0. They intentionally do null pointer derefs, triggering Windows exception handling, which they have set themselves up to handle. And they take care of the exception. During exception handling, a process can modify any register, has direct access to all the hardware debug registers, EIP, etc. It can add to EIP. You can use this as a form of indirect jump. While you're in your exception handler, add 1,000 to the instruction pointer. So you're cruising through the code. You may gloss over the fact that a null pointer deref takes place and think the code continues, when really, in that handler, they've jumped code somewhere else entirely. They can reach in. You say, I don't want to set software breakpoints. I'm going to use hardware breakpoints. They trigger an exception. They can manipulate the breakpoint registers. They can zeroize all your hardware breakpoints. You'll never hit them. Okay, so there's a lot of different things that they can do. The big trick is, and the terminology that you may hear is detecting the original entry point. We've added on this decoding, deobfuscating, decrypting stub. It's going to run. When do we get to the original entry point? Because when I get there, then I'll stop and I'll take a memory snapshot. So all these tricks are designed to prevent you from knowing how long to let it run. When am I going to get to the original entry point? Because they don't want to be snapshot. What else? Legal issues. There's always the legal challenge to overcome. And again, question?
Before you get to legal issues, can I ask a question? Have you ever had situations where you were dealing with, say, telecommunications protocol code that was written as a state machine? And what kind of luck do you have in disassembling that?
Let's think. So I've seen state machines, and you have to just sort of draw diagrams and try to figure it out where it is. A more interesting case that's sort of similar is what we call virtualizing obfuscators. Okay, so think about a Java virtual machine and the code that you as a Java programmer might write. That code compiles to a class file. So if you're a Java programmer and you say, well, what executes? You say your class file executes. Your class file doesn't execute on that system. It's interpreted by the Java virtual machine. From the CPU's perspective, it's that Java virtual machine that's getting its cycles. Okay, so that's really a state machine, right? It's a software CPU. So virtualizing obfuscators take your original binary and treat that. They write a bytecode interpreter around the x86 binary. So that gets dropped in your lap. So what you end up looking at is a software CPU, and you do all this reversing and reversing and reversing, and all you learn is the instruction set for the software CPU. Then you have to dig in and find where's the bytecode that's being interpreted. Right? So there's a second reverse engineering problem on top of that. And so it's a different type of state machine, but it can be done. In fact, one of my examples right here, this is a virtualizing obfuscator called VM Protect, Virtual Machine Protect. And you can see what IDA shows us, which is not much. Right? IDA falls apart at, it gets to this pop. In fact, it's got bytes defined in the middle. We jump around down to here, and then you get this into instruction. Anybody even know what that means? I have no idea. Right? I've never seen it before. And because it's so uncommon, I would say that that's probably not the real instruction right there. IDA has lost track of the instruction stream, and we're out of luck. It turns out if you stare at this thing long enough and try to figure out what it's doing, this call here is really being used just as an absolute jump. Right? So we follow the call. IDA just assumes that call's returned, so it tries to disassemble the rest. So we go to the call. They push some flags. They do this. They call again. Push some stuff, jump, push all. They do a lot of stuff. And it's extremely obfuscated flow. They calls are really jumps. They're just piling stuff on the stack, which sometimes they remove, and it gets kind of nasty. IDA can't find really any functions. We can't graph this thing. Okay, IDA can only graph functions, so I can't use a graphical viewer to try to say, show me the flow here. And so we have to try to unravel the state machine. And so I wrote an IDA plugin, and ultimately, it shows me that state machine after it runs a little while. Okay, so that's the graph of the state machine. And each, in the sort of the columns going across, it's got 256 opcodes. Those are the opcode handlers. All that branching is sort of one big case or switch statement that farms us out. The opcodes to the right sort of return quickly and loop back up to fetch another bytecode. And the opcodes on the left come down to go for some checking. It does some heap checking. They look for heap and stack overlap. Fix that up before returning back to the top. But that's the state machine. And I don't know anything about what's being run on top of it, right? All I've recovered right there is the equivalent of the Java virtual machine. And I've still got to go on, and now I've got to find the class file. Now that I know the instruction set, and try to reverse engineer the class file with an entirely new instruction set that IDA knows nothing about. Okay, and this is sort of the state of the art in obfuscation. Question?
You use the Solvay malware code. Where did that originate?
Where did I get that, or
No, I mean,
who wrote it?
Where was the code written?
I'm going to throw out Russia.
How do you use the reverse engineering, or maybe using this graphic, gives you indications of where the malware is coming from?
That's harder to do, but one thing that you can look at sometimes, it varies from binary to binary, is you just run strings across the binary. And I apologize for the small font. That's it. IDA won't let me make that any larger. But that's a list of extracted ASCII sequences. And more or less, I know some of that looks like junk. That's just because of some of my settings. So you're looking in this stuff for any clues of origin. And so how do you profile the adversary? Well, if you can tag what compilers do they use? And so we can profile the executable, see what compiler. Maybe they have a pattern of using a particular obfuscator. Maybe they have a pattern of a particular communications. We look for any embedded IP addresses, domain names, etc., resolve them. Where do they call back to? These call back to China. Surprise, surprise. Okay. There I go. So strings, things like that, things like, what was it, the I love you virus, it had what, I love you embedded in it, something like that. I mean, that's how that got its name, but it wasn't necessarily attributed to anybody. Sometimes people put their hacker NIMs into these things. That's kind of silly, but they do it. It's harder to tell in compiled code. You look for misspellings. Sometimes there are regional misspellings. You say, this word is spelled the way that people who learned English in Asia tend to spell it, as opposed to, say, people who learned English in Europe. So there's some different ways that things are spelled, and you can look for those kinds of things. But it's really hard in binary code to do that. Other things that you can look for are version strings, copyright strings, some of these things that the Microsoft compiler throws in there that people may not strip out. Maybe time zone settings. GMT -8. Lands you somewhere interesting. I don't know, 18. I don't know which one it is. +8. You see that more in document-oriented malware. Because Microsoft Word and Adobe Reader or Adobe Acrobat or things that generate PDFs tend to pile a lot more information in them about the tool that was used to create it, who it was licensed to, things like that. Sometimes you do see strings in here that, especially like in PDB, project database files that come with Microsoft, or any debugging information, that will be something like /rootkit /my name / whatever, and that name is clearly of Asian origin or something like that. But because C, Java, they all use English language keywords, and format strings a lot of times are English. It's sometimes hard to tell. It's often hard to tell. Okay, if you build up a body of malware, who's Mandiant's APT1 report, right? They had a large body of malware, which they were able to sort of bind together because similar coding patterns were showing up across the body of malware. And they could couple those with behaviors, right? We found this one, this was active at this time of day talking to these servers, and they were able to bind them together, not just based on what they were looking at in the binary, but based on other information that they had from monitoring the behavior of the binary, to whom it was talking to, when it was talking, etc. Yes?
Essentially, you're saying like you can do that DNA testing where you say these people are related to those people because they have this one mutation over a period of
That's
time.
exactly what you do.
Yeah.
In fact, Halvar did a study a number of years ago that was genetic comparison of virus families. And he had a whole tree of malware where you had things that were 99% similar, 98% similar, and he was able to take a huge pile of malware and basically group it into just 3 malware families. They were all sort of related. And when you start seeing that, you can say, well, there's code sharing going on here, right? So if I know that this guy wrote this one, then these guys are his friends, right? So there's some access there that is beyond just cut and paste off the internet. And that's what, when Kaspersky comes out and asserts that Dooku is related to Stuxnet or whatever, that's the kind of thing that they're doing. They're saying there's similar coding patterns going on here. Not that we found them in the same place or doing exactly the same thing. Okay, legalese. I'm not a lawyer. The 2 things that can get you in trouble are EULAs, and there's actually case law on that one. Bowers versus Bay State Technology, they said that the EULA was a contract. There's a lot of contention there because it's like a one-way contract, right? The manufacturer's binding you to something to which you never really agreed, other than the fact that you peeled off this piece of shrink wrap. So I think there's people, that happened back in 2003, and there's people looking to challenge that further, but so far it hasn't been done. You see lawyers getting thrown at reverse engineers all the time, almost always citing the DMCA, which I don't think applies in most cases because you're not violating copyright. There's no intent to distribute. Usually you just want to know how something works. I'm not sure how, this is just me speaking, I'm not sure how the act of trying to learn how something works constitutes violating anybody's copyright. Okay, but there are cases where if you're removing protections, circumventions, whatever, so that you can distribute, etc., that gets into a dicey area. But in general, the DMCA is often misused because what they're coming after you for is not a copyright violation, right? It's either not copyrighted works or etc. So sometimes people get weary. I don't ever bother. I just take it apart.
Well, speaking about legalese, you ever do any compact computer reverse engineering stuff?
Compact the company?
Yeah.
No.
They're the ones who broke the IBM out, so you can do third-party PCs.
Okay.
They did it by reverse engineering by taking a bunch of university students, and the first thing they would ask is, have you ever seen an IBM computer? If the kid said no, they go, okay, if I give you the specs and guidelines, can you build one?
Yeah, you're on that team. If they said yes, you're.
Yeah, that was,
Yeah.
Compat was the first one to start doing reverse engineering like that.
Yeah, doesn't surprise me. PC clones and all that stuff. Where are we? Almost done. For the future, right? What do we need? What's out there? There's some decompilers coming down the pipe. Again, the C4 decompiler I just saw announced just yesterday. Don't know how effective it is. They make some bold claims. It'll be interesting to see how that evolves. It can save us all a lot of money. if it turns out to be a useful tool. They claim to be able to lift virtually any x86 code regardless of how it was built. It might be compiled Delphi. It could be compiled Visual Basic. They try to lift it back to C, okay, regardless of the underlying structure of the code. That's something that Hexray certainly doesn't do because it's largely based on compiler signature matching. And then this plugin called the IDA decompiler, which is an add-on to IDA, much like the Hexray's decompiler is, also claims to do decompilation. It's another one. It's fairly new. I haven't had a chance to check it out. But it's nice to see free stuff bubbling up to the surface. New free disassemblers or break-in the stranglehold that IDA has. There's some intriguing tweets came out. If anybody follows Aaron Portnoy from Exodus Intel, he's like, first step towards freeing myself from IDA. Right, that was a tweet he had about 2 days ago, and everybody said, "What is it? What is it? Are you going to release it?" And so he's, works for a company, and so he's, they have the internal battle: is it going to be released or not? Hey, I think that there is at least some other disassembler coming down the pipe. I'm not at liberty to talk about it right now. We hope it'll happen pretty soon. That could give IDA a pretty good run for its money. That's used by a lot of people. And beyond that, there are other tools. What about that last step? What about getting from source to design documents? The only things out there that you might find are things that take source and try to generate like UML diagrams and give you these class relationships. But that's just, that's relationship diagrams. It's not necessarily, it's not really behavior diagrams. It still doesn't give you back the requirements. Okay, so it's still a lot of human in the loop. I don't think we'll ever get to the point where we're going to have an automated system that looks at a binary and says, here's your requirements document, hand that off to somebody to re-implement. It's just never going to happen. Right? We can't even, the grossly simplified example I always give is we can't write one program to tell us whether another program halts. Right? Turing tells us this. Right? If I can't tell you whether a program halts, how can I tell you that it does anything more sophisticated than halting? It seems to be an intractable problem. Right? So that's all I have. I can do demos all day. I can play with IDA all day and deobfuscate all day, but that's all I have, and I'm happy to take any questions. Thanks very much.
20%.
What's the most interesting thing you've reverse engineered just for fun, from home, or?
VM Protect, Stuxnet, I got Stuxnet on here. Stuxnet was fun to look at. Any obfuscated thing I always think is fun. It's interesting to see the fail that creeps into these things. When Skype first came out, they had a Linux client, they had a Windows client. The Windows client was heavily obfuscated, so I went to the Linux client, not obfuscated at all. Right? Give it a try. If there's more than one product, go to the one that's easier, right? At the time, there were no powerful Linux obfuscators. Right? So if they got a Linux client, you go look at the place where there's no obfuscation known to be taking place, then odds are either they've invented an obfuscator, which would have been interesting, right? Or they don't have one, which lets you get to the protocol right away. What else was interesting? Yeah, anytime a new obfuscator comes out, and you see all kinds of interesting things that happen with obfuscators. Question here first?
From your F18 example, did you find that calls to and from hardware could be easily identifiable?
Let me think about that one. Yeah, because what were they doing? So somebody asked me to come advise them on it, and they had a little bit. Actually, they had done some hardware reverse engineering, so they understood how things were mapped out to some memory mapped I/O areas, some UARTs and things like that. So they had some address ranges, and it turns out it was doing all memory mapped I/O. So once we had those ranges, it turned out it was pretty easy to tell what was getting written where and when. But they weren't doing any, no interrupts. I mean, they were handling interrupts, but there was no kernel, right? This was it. It was just, firmware, and there was no user kernel separation. So the key there was getting the memory map. Question down here?
I was just going to ask about the obfuscation on the different platforms. If somebody wrote Skype with an obfuscator on Linux, would it be like that, which is on the Windows?
The Skype or the obfuscator?
The obfuscator.
It depends on their sophistication. So there is an obfuscator. It's called UPX. It's the most basic obfuscator out there. It's just a packer that some people use across platforms because it's available on literally every platform that's out there.
They look the same.
They look similar, right? Each operating system has a different startup mechanism. So one of the things that happens when you obfuscate is when you have a dynamically linked executable, right, you have to advertise to the operating system loader what shared libraries you need, right? You've got an import table. Okay? I use these libraries and I need these functions resolved. Whether they're resolved by the loader or whether you have some lazy linking mechanism in place like Linux does, you still have to advertise that fact. So one of the problems with obfuscation is that the obfuscator hides that import data from the operating system loader. So the operating system doesn't load everything that you might need for normal operation. Okay? And so the loading mechanism is slightly different on Windows than it is on Linux. And so where the obfuscators differ is that once they have unpacked, decoded, whatever, the next step they have is they've got to get some libraries into memory somehow. And so there's the Windows way of doing it, load library, get proc address, and then there's the Linux way of doing it, like DL open, DL sim, things like that. And so, you differ when you get down to that way, and whether you need to look up everything or whether you need to leave it to lazy linking, et cetera.
So even though they have the same obfuscators on the different platforms, they'll have a different output or input.
They look different, but the unpacking, because UPX is just a packer.
Right.
So the unpacking algorithm may look the same.
Okay.
Okay, but if they're doing other things, so I'm using it. Am I using it too much time? Let's keep going.
That makes sense.
So
makes sense.
some other things that you may see, like the anti-debugging techniques, are totally different because debugger detection is totally different on Linux than it is on Windows.
Okay.
You can do interesting things. You can do what we call self-debugging. Right? Try to attach to yourself, and if it fails, somebody's already attached to you because you can only have one thing attached as a debugger at a time. And if it succeeds, then nothing can come along and attach to you later. Right? So that's the ptrace mechanism on Linux, and that's something entirely different. The Windows API for doing that is entirely different. Instruction, signals versus SEH on Windows, very different.
I don't know this Windows you talk about.
Anything else?
Um,
Okay, thanks.
Prize giveaway, if you win something that won't fit on a plane. Which one
We can win prizes too?
oh yeah.